So I'm going to talk about the role of relativistic corrections to the Sunyaev-Selvdovich effect on the Planck power spectrum and number count analysis. And in particular, I'm going to talk about two papers, one which is still in preparation, which Aditya Roti is leading, and then a paper that just got published, which Mathieu Remazet was leading, and we submitted last summer. So, of course, everybody is really surprised that I'm talking not about spectral distortions, because obviously Rashid gave a really beautiful lecture yesterday, and I think there's hardly anything to really add to this. I'm still in love with spectral distortions, and I think this is really, really cool science, and there's lots of interesting signals, not only in terms of expected signals, but also discovery space. And it is really exciting, especially with, after many ideas have been proposed, thinking in connection with Aseem Barrett about this as well. So that was just a small disclaimer. Really, spectral distortions is great, but let's forget about this right now. Obviously, I'm talking about the spectral distortion as well here, but it's the Sunyaev-Selvdovich effect, and you all know about this, that this is a great cosmological probe, and the KSC, the thermal SC, there's lots of beautiful reviews, and since everybody has seen all this introductory material, let me just advertise another comprehensive review, which we just finished, in collaboration with a few folks on the SZ signals. And there the focus was much more on high resolution, high sensitivity measurements of Sunyaev-Selvdovich effect. And we also tried to illuminate some new directions which could be, one could go in the future, and also the connection directly to simulations. Okay, so thermal SZ measurements are now routine. We have from Planck, and also of course from SPT and ACT, we have many clusters, and we heard yesterday that there's more clusters are going to be published and released, but we're talking about like order a few thousand clusters now. Here's the Planck cluster map, and we also have this beautiful measurement of the Y map. So using the Planck data, here's the NILC map, which Mathieu Remazet was producing, combining the frequency channels and teasing out the Y distortion map, which is one of the really interesting new products as well of Planck. As Francois was highlighting today, the lensing potential map is really one of the great interesting outputs, but also this Y map is really highly interesting and has been allowing a lot of scientific studies. So, and you all know about this story, of course, that using the clusters, the detected clusters, you can do number count statistics, and using the Y map, you can do power spectrum analysis. Just the typical things. Here, the number counts, where you are deciding what kind of cuts in the signal to noise you're doing, and you bin the clusters at different redshifts, of course, using a combination as well as X-ray measurements, and there is some tensions of the SZ-derived values for sigma 8. We all know the story with respect to the hydrostatic mass bias, and we heard yesterday a bit about this as well. There's lots of small details and aspects, and depending on what kind of combination of data you take, you get different answers. I don't want to go into the details of these kind of discussions because it's very complicated, and I'm not qualified to even really comment on that very much. But I want to really ask the question: what is the role of relativistic SZ in all this? So relativistic SZ, first statement to make. Normally, the classical formula assumes that the velocities are very against c, the speed of light. But when you have a 5 keV cluster, then the thermal velocities can already reach a fair fraction of the speed of light, right? And in that case, the scattering event is no longer just a small little shift. You get asymmetries becoming stronger. So the SZ signal, the black solid line showing the non-relativistic case, the main effect is that the SZ signal for a given fixed Y parameter, here it was chosen 10 to minus 4, shifts upwards more and broadens. Okay, so you get a slightly higher efficiency of scattering, upscattering photons in each scattering event. So this is all well known, but I want to highlight, of course, that the high frequency channels are actually really the most important for understanding these kind of effects. And to illustrate that, I just calculate here the purely the relativistic correction signal, just subtracting the non-relativistic case from the calculation. And here is the shape of the relativistic signal for 5 kV, 10 kV, and 15 kV. If you now rescale, just by some factors to match the 10 kV with the 5 kV and the 15 kV, then you can see that at low frequencies everything is basically degenerate. You can just have an overall renormalization of the effective Y parameter, and at high frequencies that's where you get some information. Obviously you see the differences are not huge, but that's where the real information lives in terms of distinguishing relativistic SC, and notice as well that around the null there's hardly any change in the spectral shape as well. So measuring just the position or things like that, you know, it's clear that the information comes from high frequencies. So high frequencies are needed, and this is of course also where dust contaminations are really, really strong. I just want to, before going now to the number counts and Y distortion, Y maps, I wanted to also highlight it's really important to calculate these relativistic corrections correctly, because here is a figure from Fourier, and you can see that the shape of these high frequency part is quite a bit different from what you actually expect from the full calculation, and SZPAC, which you can find here on my webpage, is actually taking care of that accurately. So that was just advertisement to some extent again. But let's go to the clusters that Planck is actually using for the number count statistics. So these clusters are fairly massive. Here's, as a function of redshift, what their masses are. It's something like 440 clusters. And when you just take simple scaling relations, you know, following Arnaud et al., or you know, things that are used by default in the community, and just paint temperatures on this, then you see that a lot of these clusters are pretty hot. You know, you can go to quite high temperatures, but you know, in this ballpark, you're talking about like 5 kV is a very common number. Yeah, so cluster temperatures, which are used for number counts, are pretty hot, or at least relativistic corrections should become noticeable. So another way of showing this is if you just take all the clusters in Planck and stack them, and just calculate the stacked average spectrum in clusters. So this is some work that Jens Erler and Kaustuv Basu and myself did together with Frank Bartholdi as well, where we basically used, you know, the Planck second Z release catalog and just stacked everything. Then you can find the average Y parameter for this is something like 10 to the minus 4, and also the average temperature, relativistic Y-weighted temperature is something like 4 kV, but the error bar, of course, is pretty large. And this shows that when you do this average stacking, you're talking, you know, about a very insignificant detection, of course, of relativistic SC, which is, by the way, in contrast to some of the claims that Fourier was making, where he claimed that 5 sigma detection is possible. I think this is coming from the fact, again, that the high frequency part, which is dominated by things related to dust and far infrared, that it's pretty difficult to actually disentangle all those things, and depending on how you do this you can get results which are you know, they are at the threshold of being detectable. And if you take the hottest clusters, you find something like 6 kV. So the bottom line, again, this is just an illustration, is that clusters are pretty hot. They're not, you know, 0 kV, which is basically the assumption going into the non-relativistic SE formula. Yeah. Okay, so now another indication what you could be expecting is just if you take the standard CMB power spectrum for the Y distortion, which you can calculate following the formalism of Komatsu and Selja. Just here the standard formula, you have seen this many times, and you then ask the question, what is the contributions to the Planck power spectrum at different L ranges? Then you can see that, you know, in the L range where Planck is sensitive, there is actually quite massive clusters again contributing dominantly. And if you do this, this is from a paper from Réfugié, when you do this in different temperature cuts, again you can see that the typical temperature in the regime where Planck is sensitive is something like 5 kV or above. Yeah. So bottom line again, clusters which are relevant for the analysis of Planck have 5 kV or more temperature. Yeah. So now the question is, does this, you know, affect the Y distortion analysis, for example, for the power spectrum or for the cluster number counts? So how is the Y map obtained? I'm not qualified really to talk about this because I've never analyzed a map in my life, but Mathieu Remazet is of course really an expert on this, and he has been obtaining the Y map for Planck. So this is a slide which I took from one of his talks, where he explains how you do this. You simply have a model idea for the data where the Y distortion signal and frequency is modeled with a non-relativistic SC formula, and you have the noise and foregrounds in the other bucket, and then you do a weighted average of the different maps where you constrain the weights to give a unity response to the Y distortion signal and minimize the variance of the maps. And then you basically obtain a recovered map, and that's what is done in Planck. Okay. Now, if the signal indeed is not for a zero temperature, basically the formula you have to use is actually non-zero temperature, then immediately just running through the same thing, that means that you will get a bias factor in contrast to here. This is an unbiased estimator, but here you will get a biased estimator. And that means that the Y distortion map is actually not the real recovered Y distortion which you would want to have. And it turns out that this bias is smaller than 1. So what is the effective effect on the Y parameter? What we find is that for 5 kV, you have a 7% underestimation of the Y parameter. So just simply, how can you understand this? It's actually consistent with thinking of the 353 gigahertz channel driving the result. And if you just look at the effect, you see that for the non-relativistic, you have the amplitude is a little higher than what you would have for 5 kV. The effect is roughly 7, 8, 9% in fact. That means that for a given flux, you need a larger Y parameter to compensate to actually get the same answer in terms of the intensity. Yeah, and this is consistent with an analysis that we did as a subsection in Jens Erler's paper, where we also concluded a similar thing, that you would actually, neglecting Y relativistic corrections, you would get a biased result for the Y parameter. And the effect, of course, depends on what kind of frequency setup you have and sensitivities, but also the ability to subtract foregrounds. And Aditya is working on this now a little bit more carefully, but here you can appreciate this immediately. If you look at high frequencies, the effect is, of course, an overestimation, an underestimation. So here it's an underestimation and it's an overestimation at higher frequencies, and it's an underestimation around low frequencies again. Yeah. So anyway, the bottom line is there is an effect, and if you do the Y distortion map and just calculate the power spectrum, then you see that the CLYY actually increases, the reduced CLYY. The effect is something like 15% if you assume 5 kV cluster temperature on average. And I will get to that point in a minute. And if you then translate this, just knowing that the sigma 8 dependence of the YY power spectrum is something like a sigma 8 to the 8th power, pretty steep, you find that this corresponds to a misestimation and underestimation of sigma 8 by something like 1 sigma for 5 kV. So that means that you in principle can shift the centroid of the constraint towards the CMB preferred value. But of course, this is, depending on what kind of temperature you have, this is not the full part of the story, but it is part of the story. Yeah. So I just said here as a ballpark 5 kV, and I mentioned 5 kV many times. But let's ask the question: what is actually the real temperature we should be using? So for the first statement is, if you do stacking analysis or a single cluster, then the relevant temperature is the Y-weighted temperature, because you're basically just looking at the relativistic correction as a perturbation around some mean, and you get just a linear average of the temperature with the Y parameter. That's what you get. This is well known. If you, however, do a power spectrum analysis, you actually have a Y square-weighted temperature. So you can think of this as you need to weight by the power spectrum itself to obtain what is the relevant temperature at the corresponding scale. Yeah. So one can formally write this down. It's very simple to show. And what does this mean? Well, first of all, you can efficiently compute this within the Halo model, which is also used for the power spectrum calculation. So this is easy. I'm going to show you in a second. And it also means that higher masses are upweighted, because you're, of course, having a higher, the higher masses have higher Y parameters, so you're actually upweighting things. And it turns out that it is a scale-dependent quantity, so it's an L by L statement, but for the simple estimates with Planck, it's actually sufficient to use 1 temperature. as I will show in a second now. Okay, so here is what we obtain using class Z, which is a code that Boris Bourlier was developing. He has actually used this code as well to do some analysis and show some of the degeneracies of parameters together with Eiichiro Komatsu in 2017. The result you obtain is the black solid line is what on average we would obtain by just using the simple scaling relations. The green band is kind of indicative for what kind of average dispersion we expect just from uncertainties in the scaling relation. Now this is just very rough. There is large uncertainties, but you can see at small scales, high L, the effective temperature is low, because as I showed you, at small scales, very small halos contribute, so the effective temperature drops. If you go to larger scales, lower L, you see that the effective temperature can go up to something like 9 keV. However, at very large scales, you also expect the diffuse contribution from Y to become dominant, and then you're basically downweighting it again, and that's what is indicated here with the, I'm nearly done. 10 minutes, wow, I'm really fast, great. You can see here the band, which is just showing an effective downweighting coming from the diffuse Y, which you could be present at large scales. So, but bottom line again is around Planck temperatures, where Planck is sensitive, which is this band, you can actually expect at least 5 keV. It's even conservative to assume 5 keV from these estimates. And now there is huge uncertainties, of course, in these scaling relations. One, and everybody knows about this, one is that X-ray temperatures are, of course, biased with respect to Y-weighted temperatures. They can be either low or they can actually be high as well, depending on if it's a cool core cluster, etc., etc. So this is huge uncertainties there. But still, I think it's fair to say that 5 keV is not totally unexpected for the Planck analysis. Okay, so this means that the tension between CMB only and SZ-derived sigma 8 constraints is definitely affected by these relativistic corrections. It goes in the right direction, so it alleviates this tension, and it's not only a shift. We only talked about the shift, but there's also a spread because of the uncertainties in the scaling relations. So that means it actually increases the error bars probably as well, which means it will probably help in addition, making these kind of these constraints, bringing them together again. Okay, so here's a slide which is just a preliminary result from Aditya's work on the number counts. You can do the same game there. It's a little bit more tricky, and that's why I'm also at this point not ready to make any concrete statements, but you can see the following thing. If you just naively rescale the Y parameter, that means, of course, that the signal to noise goes up if you assume the noise stays the same. I will come to that in a second. And if you then just make the number count curves, you can see that, the number count curves, and this is, Aditya did this himself with the data, so he confirmed the Planck cases for the number counts, but then the solid lines are the ones which are coming from his rescaled version. And the interesting thing is, of course, that you're at the threshold where you're, you say you put your signal to noise cut at some value. When you're below the threshold, you can go above the threshold. That means you increase the number of clusters which are in your, signal to noise bin. And that's the reason why you can change these number counts. And if you look at this, it even changes to some extent the shape a little bit. There seems to be like an indication for a peak now, which is actually something you would expect from the theoretical calculation. Now there's caveats, because assuming that the noise is constant is not correct. If you just take a simple single channel estimate, you can, on the back of the envelope, show that it should actually be remaining constant, the signal to noise. However, the scale radius also changes, so we just estimated all these things, and Aditya is now really working on extracting these, doing a source extraction with these relativistic corrections included. But it seems that there is actually an effect because the scale radius is changing, and that means you are actually leaving the signal to noise, you're actually increasing the signal to noise. So the bottom line is, again, there is an effect, and it moves in the right direction because it increases the number counts, which means you're again helping, and we found a 1 sigma effect, but this is preliminary, and I don't want to really, push this at this point. Okay. since we're talking about the future as well, what is the future opportunities with relativistic as Z? We will have tens of thousands of clusters in the future, and they will be measured with unprecedented precision, wide frequency coverage. I mentioned the high frequencies, how they are really important for RSC. So this will be something that we hope to get. And here's just, CCAT prime, millimetron as as some long-term, and also pico. Those are interesting experiments in this direction. And SO will, of course, have many, many clusters to play with. But SO is limited more to the low frequency part, where you will probably not have the way to internally distinguish RSE from normal SE effects. So you will have, but then of course there's all these combinations you can do with X-rays and lensing measurements, and it's nice complementary tool to do cluster studies. So then there's of course the three paths. One is individual studies. We will really be able to measure the temperature and maybe even the temperature profile on individual systems in the future. Maybe even velocity maps. That's a little bit of, that's of course very challenging, but we will be able to do reconstruction of cluster profiles and look at non-thermal SZ. These are really interesting aspects. Then in terms of the stacking analysis, and I'm done basically in a second, we will be able to do RSE in mass bins. And that means we have a self-calibrated mass temperature relation using really SZ observables, which is of course really interesting. And then there's the statistical avenue, which is related to the power spectrum and number count statistics, which I have been highlighting. So I think all of this is really important and interesting to look at, and of course very relevant for when we are thinking about using clusters for cosmology constraints on neutrino mass and sigma 8 and dark energy. And here's my conclusions, with the main bottom line being that I think RSC is starting to play a role in Planck analysis. We see an effect. It's not detectable for individual clusters or even stacked clusters, but it is on a statistical level significant, and you can actually see that this helps alleviating some of these tensions, and I think it's interesting to think about this. Thank you.
All right, any questions?
Yes, you certainly checked, because people are trying to use kinematic effect to see how it influences.
Right. Yeah.
Yes. Yes. It is. I think it is very good to add to your pictures just in which direction both are working and how much one of them is weaker than another.
On average, the KSC will, of course, average out if you do power spectrum type analysis and so on. So I think that the contributions are smaller in total. Yes. But of course, I agree, there is contributions, and we need to very carefully look at this and do this more properly. For the stacking, for example, it's clear that on average you get no KSC contribution. And we didn't use that assumption, but we basically, it is something that we actually also saw with the stacking analysis that Jens Eller did.
Because the stacking analysis seems there are results confirmed by
yes.
by
yep.
SPT and by Planck. Everybody sees the KSZ. Question, I think that it's important to compare and to see are they working or what, where one is more important than another.
So, in addition to the average temperature that you show us, you also have non-thermal effects as well. So, in some sense, this is kind of conservative, right?
You mean in terms of the temperature could be argued to be higher, or?
Well, you will have additional corrections from the non-thermal effects. So, it would mimic an even higher temperature, or.
Now you mean turbulence pressure support?
For instance,
that's correct. And one needs to, as I said, we need to look at this carefully. But here, the idea is that you can actually, in an L-dependent way, you can say how the power spectrum should be changing. It's basically a shape change of the power spectrum, if you will, the effective power spectrum of the Y parameter.
Right, Rishi?
So the sigma 8 shift Is it just analytic estimate or it is coming from parameter estimation?
So at this time, you just did analytic. It's really, this is
Just,
the mean
yeah.
shift. And if you do the, so we did some MCMC, but we didn't put this in the paper. You see this effect. And
It will be interesting to see how the plot shifts
Exactly, yeah.
with this.
yes, and in particular, when you include as well the uncertainties and the relations for scaling, you put some parameters to actually say, well, there's uncertainties, then you have to marginalize over those. And that's why I'm saying the error bar is supposedly also going to go up a bit.
All right, any last questions? And if not, let's move on to the next speaker. And thanks, Jens, again.